next lecture is by Joaquim Serra. You have heard his name already several times today. I have to say very few things about him because what will be interesting is his talk. He has undergraduate, master's, and PhD degrees from this university. The PhD was advised by Chan and Poleris-Nabarro, as you know. He was also a student of, I will translate it to English, I don't know if this has been done before, of the Interdisciplinary Center for Higher Studies. You would say advanced studies, but maybe it would be misleading. And I think that he then went for the postdoc with Alessio in Zurich, and now he has a position at ETH. Please.
Thank you very much, Sebastian.
Your title, right?
Yes, the title anyone can read. Thank you for the introduction, and thank you for giving me the opportunity to speak here. And it's very nice to celebrate this PhD honoris causa, doctorate honoris causa of Alessio. So I will talk. So when they asked me this to give a title for my talk, I gave this one that I have used several times, and I liked it. But later, I realized that I have been a bit too ambitious. So since Sebastian didn't say, I will read the title, Stable Interfaces from Non-Local to Local. Okay, I will explain, I will spend most of my talk explaining what stable interfaces are, or what I mean by this. And this, from non-local to local, will come at the very end, if time allows, and I'm not so, but okay. And I like this, I chose this topic because it's, you will see it has a lot of Alessio, and also it has a lot, I would say, of UPC, much even, and of the group in mathematics in PDs in the UPC, and you will see a bit why. Let me start. So, interfaces. So let me talk a bit about physical models for interfaces. So what do I mean? This is not a very official word. This is more a heuristic word. What do I mean by interface? I'm in a situation where you have a volume that is occupied by two competing states, or two, let's in plain words, two different things that exclude each other. So this is very vague, so let me be more precise. So the two things could be, as in Xavi's talk, ice and water. So you are either ice or water, not both at the same time, right? It could be two, sometimes in some situations, two types of bacteria that kill each other. So only in some part of your plate, only one of the bacteria is alive. Or two fluids, as in the lava lamps of my title slide. Like when you have two immiscible fluids with the same density, they tend to aggregate, and they form these patterns. And there are many more examples. I'm being super generic because I want to include a lot of philosophical things in this picture. Okay. And mathematically, the picture is like this, is black and white, and with this we are happy and we can do things. Right? State 1, state 2. So the interfaces is, so usually as Xavi showed us in the case of ice and water, here we will have a PDE. So things are boring inside of the black or the white part. If you look inside, things are boring. It's a linear PDE, so easy stuff. So what is nonlinear, very nonlinear, and interesting is the evolution of the interface. That is what is in between. And this is, depending on the problem, they are called free boundaries, phase transitions, minimal surfaces. Not exactly, but they receive several names, and you have different techniques, right? So, and let me see that to study. So we want to understand where the interface is generally in a class of problems that by now is very wide. And usually what you do is you cannot really write a PDE like for the interface as a graph. What you do is you consider a function u from the space Rn is R2 or R3 maybe. Think of R2, later it will be higher dimension, but R2 or R3 to R, and my interface will be a level set of this function. And this function will solve a PDE, or more precisely, typically will be a critical point, the function u, of some energy functional or Lagrangian. So since this is still a bit abstract, I will go to a concrete example that is the one that Xavi explained to us. So this is the stationary, if you want, the Stefan problem. Ice-water interface. I'm not going to write any PDE. It's a PDE talk, but I'm not going to write any PDE. So I will just give the Lagrangians. Because from the Lagrangians, you know, you compute, I will do an example, you compute the Euler-Lagrange equation and you have your PDE. But let me write just the Lagrangian. So for the Stefan problem, the Lagrangian is this one. Is a functional, you know, it's something that you give to it a function that returns a real number. And you integrate the gradient square plus this very simple function, the maximum of u1, 0, you integrate in Rn. In this case, this is your functional. And this function is very nice because it's convex, right? For another problem, this is just example. I will talk. For another problem that is the optimal design of an insulator, thermal or electric insulator, you have a very similar energy functional, but now the potential here is a bit different, and it changes the problem completely. So these are nonlinear problems and are very sensitive to small changes. But again, you understand the two regions are defined by level sets of your function, right? As in Xavi. So where u is positive here, you have the insulator, and where u is 0, you have the conductor. Or in the problem of ice and water, we have seen where u is positive was water and u is 0. So you solve a PDE, and the level sets of this PDE tell you where the free boundary or the phase or the interface is. Okay, this is a very general thing. So I have talked. We have mentioned these Lagrangians, and we said we consider minimizers or critical points of these Lagrangians. Let me make a very quick general review of what means in the calculus of variations for a function to be a minimizer of a functional. So J will be a functional, and I say it is a minimizer, U is from Rn to R. It is a minimizer of the functional. If for every phi compactly supported and smooth, I compute G of U plus T, it's a real number, psi, phi, and this now, you see, for fixed phi, this is a function of one variable. So, and what I ask is that this function has a minimum at t equals 0 for every t and for every phi. So this is very infinite dimensional, the space where it is asking, but I can always convert it in a real function just doing this trick, right? And this is very useful and powerful idea. But of course, as for real functions, so real functions not only have minima, they also have local minima that are very interesting, and they also have critical points, maybe maxima, like this. So the minimizers are a subset of what is called for, in the setting of functionals, stable critical points that is what corresponds to local minima of the functional. And the actual definition is here, but so the idea is that you could have for a function that it's really an absolute minimum, or maybe the Hessian is positive definite and then it's a local minimum. And this is the setting, essentially the setting of stable critical points. And critical points is everywhere where the gradient vanishes, right, for functions, and for functionals is the same. So usually when you compute the PDE, you find critical points, and then it's difficult sometimes to check that they are minimizers or no. When it's not difficult to check that they are minimizers is when the energy is convex. That's why it's so important. When the energy is convex, you check, you have your critical point, then you are satisfied because it's the same. The three notions, critical point, stable critical point, or minimizers are the same. So now in this talk I will care about stable critical points. Let me motivate a bit why. So, well, here is a, but I think maybe this I can skip a bit. This was a concrete example just to, so that everyone is on the same page. A very well-known example, maybe for most of you. And in case there were younger people, I had it. So if you have the graphical, so a piece of graphical surface, so x1, x2, v of x1, x2, the area functional for a graph is like this. This is the integral so this is a surface in 3D, and the area of this piece of surface is the integral in here of 1 plus the gradient b squared. This you know. And then you can, using the abstract definition I gave in the previous slide, you can compute things, very precise things. So you say, this will be a critical point, your function b will be a critical point of the area if this function has zero derivative at 0. But this I can compute. So this is the function, fixed for fixed phi. I compute the derivative at t. I put the derivative inside of the integral sign, and then I can compute. This is a computation. This is a derivative. And then there is the trick of Juan Luis. the universal trick is integrate by parts. So you integrate by parts, and you get the divergence of this times phi is 0 for every function phi, but then this means that the divergence is 0. This is the first class in the calculus of variations, right? But it's what I mean when I say functional is this, just this, right? And this is very classic, as you see, right? Oh, okay, sorry. But it doesn't count. Yes, exactly. So important remark here, for graphs, the area functional is convex. If you see this function before here, this function is a convex function. And this means that when you consider minimal graphs, a critical point is automatically a minimizer. Let me just leave it here, because if I need to say more details, I will lose time. But this is not true, and it's very important. It's completely false if you consider in minimal surfaces that are not graphs. And here is a very nice picture I found in a paper of Ito and Sato. This is the good thing of archive, right? You have access to wonderful things. So this is a paper with educational purposes, but this is the example of a catenoid. So they take two rings and they do a catenoid with soap film, and when the two rings are close, the catenoid is always a minimizer. So it's, of course, it's stable. And then you start to separate, and this you can compute analytically because it's a very easy situation. There is some point where the catenoid is not a minimizer, but it's still stable, and it survives. So nothing, you can stretch it, it's okay, you see it. The point is that it doesn't disappear. But when you reach the point that it becomes unstable, then immediately this catenoid, it's what is shown here, the neck becomes thin, and then you end up with two disks, right? So this is why we care about the stable. So unstable things immediately disappear. So noise, that Juan Luis was also mentioning noise. So noise, ambiental noise, that is, by the way, is higher in Barcelona than in Switzerland. So ambiental noise makes unstable configurations disappear instantaneously and decay towards a stable one. So in nature we find stable configurations, and not only minimizers, because these configurations are very interesting when you pass the threshold that they are not minimizers, and if we only consider results for minimizers, we will miss some people that are there and are interesting, right? So with this very general introduction, let me go to the setting of more concrete setting of two classical models for phase transitions, but keeping an eye with the time. Yeah. No, I think I'm fine. So let me say a word of what are, so we want again to model a situation in we have two states, and a trick, a very powerful trick that works for many models in physics, and because also it generalizes to more complicated situations where you not only have black and white, but you have multiple like vector valued states, let's say, like in harmonic maps or things like that. So what you do is you replace this model black and white by a function. As we said before, we will find our transition sets as the level sets of some function solving a PDE or critical point of some functional. And here in this model, the function u takes values between -1 and 1. Of course, this is a convention. I could choose between -1000 and 100, but it would be ugly. So the u takes values between -1 and 1, and it has a parameter epsilon. And now the idea is that if I cook up correctly the PDE, and this is based on modeling, and some models have some physics, and some are more phenomenological, or I don't know how to say this one. Okay, but the point is that there is this parameter that has somehow the interpretation of the width of my transition, and where I will construct some function that is -1 where the state 1 is 1, where the state is not exactly -1, is -0.99, where there is one state, and 0.99 where is the order state, and in between it has a sharp transition, right? And this is better behaved than this. And like in the same setting, there are a very famous model and maybe not so famous model, but also quite classical, as you will see. That is, the first is the Lagrangian equation, and as I said, I will not tell you the PDE. Usually, I will tell you the functional, because you will see many things from the functional, not that many. If I write the PDE, you will not be able to see probably, at least I'm not, that many things as from the energy functional. So for all in Can, you consider an energy functional that depends on a parameter epsilon, I epsilon of u, that is the h1 norm squared of u, okay, now, plus epsilon to the -2, the integral of some potential that I will say what happens with this potential. But now let me write what is the h1 norm squared in Rn. This is just the Dirichlet integral de tota la vida, diguéssim, no? And now you will ask, this is the integral in Rn of gradient u squared, and I can write it in Fourier, as we were using Fourier this morning, right? As the integral in Rn of psi square Fourier transform of u psi square, right? This is a measure of the oscillation of your function. And if you will ask, if this is the Dirichlet integral de tota la vida, why do you write it here with such yellow and complicated notation? You will understand when I present my second model, that is the Poleris-Nabarro model from the 40s, because it's exactly the same, but just that instead of the h1 norm, I have the h1 half norm, and instead of epsilon to the -2, I have epsilon to the -1, but this is just because epsilon is a length. So if you want this to have units of length, here you are doing less derivatives, and this is the correct scaling, right? But it's the same, but just I replace the h1 norm by the h1 half, and now this is not the tota la vida, this is more new. Well, it's quite classical actually, this is very classical too. But it's not in the PD courses of the degree of math. And then this is the h1 half norm square, is this double integral, so it's also an oscillation, u of x minus u of y, this computes oscillations. But in the Fourier, you see the perfect analogy. When you go to the Fourier side, you see this is only psi u square. So instead of psi square, is psi. That's why it's the 1/2 of this. So we have seen the same idea with operator, right? And in both models, the W, the potential, is what is called the double well potential, that is some potential that has this form, u minus u square square. It doesn't need to be exactly this, but to have a precise definition, I put this formula. And let me explain in the next slide what the double well potential does. So double well potential is some potential that has two minima at the two values that I said before that I want to privilege, the +1 and the -1. And what the double wall potential does to my energy is that if now I want to minimize the energy, you see I have a huge, epsilon will be little, right? It's tiny, so epsilon to minus 2 to the minus 2 is huge. I have a huge panelization on this, so if I try to minimize this, the functions that will be very close to all the time to minus 1 or 1, because if you are in between, you pay a lot. So your functions will be almost all the time close to plus 1 and minus 1, but maybe there are boundary conditions or something that force me to be here plus 1 and here minus 1, so I need to do a transition. And then near some fat surfaces of width epsilon, some transitions can occur, right? And if you want to see a bit more this, as here this you cannot complain is a PDE because it's an ODE. Right? So in one dimension, you can compute how is the 1D solution connecting minus 1 to 1 of this ODE. That would be the Lagrangian equation, and is as we were predicting. So is something that goes, it's here like minus 1 and minus infinity, and then it has a very sharp transition of size essentially epsilon. So the level set, the distance between the level set minus 0.99 and 0.99 is epsilon. And this is what is like the model 1D solution, how the profiles will look like. So, and now, so we understood that our solutions will be most of the time plus 1 or minus 1. So, but how is the transition? Now, what tells us how the transition will be is this term here, is the oscillation, the penalization of oscillation. So, and here there is a, if you want an insightful computation that tells you what the penalization will do, is that if you take a piece of a smooth surface and you consider a function that is the 1D function from the last slide composed with the distance, so for instance here, the 1D function, so this is like an answer, this is like fattening the surface and say, I take a function, let me say more simple. I have a surface and I take a function that is plus 1, then it has a ramp and it's minus 1. But I do it with the curvature of the surface. Then if you compute the surface, the energy of such a function, you will see it's proportional to the area. So this is easy to see. So heuristically, the best way to, and it's proportional because of this term here. So the oscillation term, of course, there is a constant renormalization you need to do that depends if you are here or here. It's a bit different. But the idea is exactly the same. So since you are penalizing oscillations, you need to go from plus 1 to minus 1, and you are doing a transition along some surface. So the best way to do it is if it is a minimal surface, right? And this is what was established rigorously by Modica Mortol and then Alberti Buscite for the two models, right? And if you have a very Italian and very close to Alessio school, right? Yes, Pisa. So if you have a sequence of minimizers of one of the two functionals, you can choose because they are very comparable, and epsilon k is the values of this small parameter is going to 0. The functions converge in L1 to a characteristic function. So in the limit you see plus 1 and minus 1, and the interface in between is a minimal surface. Okay, it's a minimizer of the perimeter. Okay, this applies to minimizers, and this the same by picture or by more heuristic is that if you look at Allen-Kahn or Poleris-Nabarro, the two models I described, as epsilon goes to 0, what you recover in both cases are minimal surfaces, right? And what is happening at the level of the solutions is that your solution U epsilon will look like this. The level sets, let's say minus 0.9 and 0.9 or 0.999, all will accumulate on a single surface when epsilon goes to 0, and this surface is a minimal surface. This is the idea. Okay, and this is shows a famous connection between the theory of phase transitions and minimals and minimal surfaces. And this connection for many years was used to prove results for the PD, for using results because the theory of minimal surfaces is much more classical and had been developed before. So the interaction was in the direction of borrowing ideas from the minimal surface theory and using them in the case of the PD, right? In the case of phase transitions, but nowadays the interaction is bidirectional. So because it's sometimes convenient to use these models, like the Allen-Kant, to produce minimal surfaces. And a good example is a recent paper, very recent, of Causa and Montolidis, that they construct some minimal surfaces on 3 manifolds, and this is related in relation to Gauss conjecture. And they use, it's very convenient there to use as approximations of minimal surfaces solutions of the Allen-Kant equation. And then they make the parameter go to 0 and they find minimal surfaces. Okay, I talked a lot, I presented more or less, hopefully you could understand the basic idea of these two models. And I wanted to at least to present some conjectures, because if you are not busy this evening and Netflix is not working, then maybe you can try to you have something to do. So first, a very classical problem, just remind, one of the most classical problems in minimal surfaces is the Bernstein problem, 1914. So it's very classical. It just asks, if you have, I computed for you the equation of minimal graphs. Now if you have an entire minimal graph, so a minimal graph that is a function from Rn minus 1 to R, right? This defines a graph. And that is a solution of the minimal surface equation, a critical point. Must it be a hyperplane? Because hyperplanes are obviously minimal surfaces, but there are others. So this is very classical. So the answer is there are only planes in dimension 3, 4, 5, and 6, 7, and 8. But in 9, you have examples. You have a non-planar or a minimal graph that is not a hyperplane, and all of these are very famous results by all well-known mathematicians, and during essentially the 1960s, right? So this Bernstein problem is a source of material, so a source of ideas in the theory of minimal surfaces, and it has an analogy in the theory of phase transitions, that is the De Giorgi conjecture. So this is a conjecture of De Giorgi from 1978 that says that essentially the same that happens for the Bernstein problem should happen for the model for the Allen-Kant, that is this model in phase transitions. So here you have only one surface, and here you are conjecturing things at the level of level of level sets. So what it says is the assumption that replaces to be a graph in this setting is if you have a solution of your PDE that it's monotone in the last direction, then it should have one dissymmetry, and this by definition means that all the level sets of your PDE should be parallel hyperplanes. So this is there is some clear analogy between the up to the at least if De Giorgi said at least if n less or equal than 8. And this you have positive results and a counterexample, some from people that that are in the audience. So n equal to, it's a bit, it's also always it's a bit of a special case. It's always a bit easier, the case n equal to, but n equal 3 was a very important breakthrough. It's 2000, so it's after a lot of 20 years, right? 2000 by Ambrosio and Cabré. So Ambrosio, Cabré. And then Sabin proved, and this was a very celebrated paper of Sabin, that proved the conjecture under some extra assumption that is not so small, that for all the rest of dimensions, and this is a very strong, this is a very good result. Anyway, if there is this if, but at the level of De Giorgi, he puts an extra assumption that he assumes that solutions to be minimizers. For graphs, for minimal graphs, you don't need to assume, because you can prove that any minimal graph is, by a foliation argument, is automatically a minimizer. But for solutions of the PDE, you don't have this, and De Giorgi didn't include this assumption in the conjecture. So, I don't know. Maybe he forgot, maybe we cannot ask him, exactly, unfortunately. But related to this, and this missing assumption, I want to present some very strong conjectures that are called, in the same spirit, that are called stability conjectures. That these are not for graphs, so forget about graph, and let me state the one for minimal surfaces. So the stability conjecture for minimal surfaces would say that if you have an entire object, I will not make all the list of assumptions, because some object without boundary, and that isn't entire, right? That is a minimal surface, and that is stable in all of Rn. So this is a hypersurface of Rn, right? A minimal hypersurface and an N that is complete, connected, embedded, whatever. But what means is that this doesn't have, it never ends, right? It doesn't have boundary. Then it should be a plane if the ambient dimension is less or equal than 7, right? So this is only known for stable, yeah, of course. If not, there are many, even in 3 dimensions. You have periodic minimal surfaces, you have a lot of things. No, but if it is stable in all of Rn, then it should be a hyperplane. And the same you can conjecture for Allen-Kahn or Poleris-Nabarro for the 2 models, because we have seen for epsilon going to 0, they are like minimal surfaces. So let's conjecture that the same happens here. And this. So any stable solution of Allen-Kahn or any stable critical point for the Allen-Kahn function or Poleris-Nabarro, you conjecture that it should have 1D symmetry in ambient dimensions less or equal than 7. Okay, 1D symmetry, again, I repeat, is the same, the analog of being hyperplanes, is that the level sets are hyperplanes, right? Okay, I said these are very difficult, very tough, and very strong conjectures. For instance, this is only known, or was only known for minimal surfaces in dimension 3. So 2-dimensional surfaces in R3, only result. All the rest of the dimension was open. Is open. And both statements, well, for minimizers, the picture is much simpler. You know that the statement is true for minimizers, but we saw before that there is more life outside of minimizers. And as I said, the conjecture, this one is only known for n equal 3, and this is Fischer, Colbury, and Schoen, and Carmo-Peng. And to see that this is stronger, let me just mention that if you prove this conjecture, the B, in some dimension, it implies the Giorgi conjecture in 1 dimension more. So if you prove this conjecture, this I'm not going to discuss why, but if you prove this dimension, this conjecture in dimension 3, then the Giorgi follows in R4, right? So this is strictly stronger conjecture, and even you gain 1 dimension. Okay, I think, well, I have still. Okay, it's enough. It's enough. So now, after presenting a bit the conjectures, let me try to, since it was in the title, to mention at least the result we obtained with Alessio, to state it. It would be nice. And then where this non-local to local comes a bit, and the relation with UPC of this problem, that I think it's very important. So the theorem that a bit surprisingly, I would say, at least for us, was we found when I first was in Zurich, no, it was the first year, was with Alessio, is this one. It's like, take this in 3 dimensions, right? Take a function from R3 to some interval, let's say -1, 1, it's not important, that is a stable critical point. The important thing is that this is a bounded interval, right? That is a stable critical point of some functional of this form. So you take the h1/2 norm square plus some potential, and the potential you can choose, any smooth potential. Then it is a 1D functional. It is a 1D function. So it's the same conclusion as De Giorgi, or as the stability conjecture. So the function has this form. U of x is phi of E scalar product x, and this just where E is a unit vector, and phi is a function from R to AB. So you choose a direction, and then you put a 1D function depending on this variable E c dot x. This is what you want to prove. So of course the consequences of the result is that I said the stability conjecture is true for Poleris-Nabarro for n equal 3, because you just apply to a particular potential, and the analog of De Giorgi conjecture for Poleris-Nabarro is true in 4 dimensions, because I said if you prove this stability conjecture in some dimension, you get the De Giorgi in 1 dimension more. Okay, and to end, because otherwise a bit, of course I cannot mention how we prove. It's not a very long proof, but I mean it used ideas from here and there, but to see a bit, because I think it's appropriate for this occasion, because the connections with UPC. So first, that maybe one of the first papers studying this problem of Poleris-Nabarro with this perspective of the De Giorgi conjecture and geometric, and in this respect was very pioneering, was by Cabré and Solà Morales, a very nice paper in CPAM 2005 appeared, but it's even from, this started 2002, so, right? And they did the case, the 2-dimensional case of this stability conjecture, if you want, as I said, the 2-dimensional, but more importantly, they also established some kind of methods or ways to look at the problem, right? Of the stability, both. Yeah. Yes. Okay. As I said here, and also later Xavier Cabré with a student here in UPC, then the Eleonora Cinti, proved the analogs of De Giorgi in 3 dimensions. So with Alessio we established in 4 dimensions as a consequence. So, but for 3 was proved here. And a bit, so I don't have time, but this non-local to local is just as a source of ideas to attack this problem, even if our functional in the limit is the local gives the local perimeter, right? A source of ideas to attack this problem came from the study of non-local perimeters that come from a generalization of these models. And essentially, if I have 1 minute, I can explain, because it's short. So you have noticed that, because I forced the analogy, that the two functionals have this shape, right? Some hs norm, epsilon to the -2s, integral of the potential. And now, if I choose s equal 1, I get Allen-Kahn. If I choose s equal 1/2, I get Poleris-Nabarro. So this is a natural way to find a curve of functionals, very naturally interpolating the two. But then you can say, okay, this interpolates between s equal 1/2 and s equal 1. What if you take s less than 1/2? It also makes sense, everything, but, and then this, the study of this functional, just by curiosity, by extrapolation in the beginning, led to the definition of some new geometric objects that were called non-local minimal surfaces. And in the end, it was a rich source of ideas and problems. And actually, thanks to some ideas coming from the theory of non-local minimal surfaces, we could apply to the other model that is more similar to local minimal surfaces, right? And let me mention that this non-local minimal surfaces, the theory and the analysis, and also the corresponding CMC, the constant mean curvature surfaces, many people also from UPC have contributed and are contributed with nice results to this theory. These non-local minimal surfaces is also very related to UPC, apart from Austin. And let me mention, apart from Xavi Cabré, also Matteo Cozzi, who was postdoc here, Giulio Sato, Albert Mas, who are here, Joan Sola Morales, etc. They have and are contributing to this problem with very nice insights and results. And thank you for your attention.
Thank you very much for this wonderful talk. The room, comments or questions, or both?
I already know the answer, so don't want to
So the point is that for this Nabarro is for crystals, right? In dimension 4, you can prove the conjecture as De Giorgi stated. And instead for the Allen-Kant, that is the original, is it still open in dimension 4, right? And both problems in the limit give you minimal surfaces. So, do you think that, and now you could go, well, two questions. Do you think that that you could try to prove something for minimal surfaces thanks to Poleris-Nabarro, and Poleris-Nabarro could be more useful than Allen-Kant, for instance?
Well, it's tricky, but you never know, right? This construction, for instance, in this construction I showed of minimal surfaces, it was very useful to use the variational approach, because otherwise these min-max, they don't have so much structure as when they do in the variation. So, and now we discover, like, in some sense, the half Laplacian, it looks more complicated because it's instead of, well, the half, this fraction 1/2, it should look more complicated, but in the end you are approximating some problem, and if it has better properties, why not to use it, right? In the end, in the limit you are, so maybe you have better, stronger compactness properties for your sequences of stable. I don't know. Actually, we are a bit exploring in this direction, but I can.
And can you put the transparency where there is the S parameter? Yeah, okay.
Yes.
So for S equals 1/2, you are able to prove the conjecture of De Giorgi in R4. For S equals 1, no? Are you trying to go from S equals 1/2 to S equals 1? Well, I know that you are trying. it's so tempting, but how are the...
This I will answer off the record. It's very recent.
More questions or comments? Let's take this